All right. Hello, everyone who's there. My name is Jonathan Perry. I'll be hosting the webinar today. If you can't hear me, or if you guys do have any questions, please contact us on the GoToWebinar panel. You should have a tab called Questions. Once you submit a question, Lamia, who is a colleague of mine in the Berlin office, if you haven't met her, will be answering questions either at the time of the question, depending on what it is, or at the end of the webinar, we'll be answering questions related more specifically to the talk. If anyone can't hear me, just so you know, you are muted, so I can't hear anyone and we won't get any crosstalk. If you can't hear me now, please indicate that either through the questions tab or the chat page. Aside from that, if you are ready, and let's see, here we are. If you are ready, we'll go ahead and get started. On this moment, let me just get one moment just to verify everyone can hear me through Lamia. Let's see, Lamia, if you can send me a Skype. Okay,
yes,
perfect.
Yeah. Hi, I just wanted to say hi to everyone as well. So we are waiting actually for a few more people to join, but maybe you can slowly start.
Okay, we can give it, let's give it another minute or so, and then we'll come into it. I hope everyone is having a good day. I'm over here in Texas at the moment. Dr. Yavluchansky, I know you're just north of me, and we have several others. We also do have many NIRx employees attending as well. And Dr. Yavluchansky, I'll come by as soon as I can. I was just telling somebody to go to OKC as a, he's an MD PhD here, in fact. I was talking to him this morning. I told him to drop by your lab when he got a chance.
There is also this option, I don't know if you can see it, to raise your hand if you have your question. So John and I are not really able to monitor at the same time the question, the poll, the chat, and the raised hands. So maybe ideally don't use the raise hands option. If you have a question, just type it in. So we will monitor that and answer at the end of the presentation.
Okay. All right, so I'm going to start moseying on through this. Again, if you do have questions, just feel free to ask them on the spot. It just may take us a while to get around to them, but I'll go ahead and get started on this end. Let me just clean up my screen here. Lamia, do I have full screen? Nothing's impeding it?
Yeah, let me check. Looks good, yes.
Very good. All right. So I want to give a little background about myself. I want to do this specifically because this is kind of the reason why this presentation has begun. I started out actually in a wet lab working with mouse and rat tissue. I had absolutely no computer background whatsoever, and I eventually left that lab. And in scurrying, I convinced myself I wanted to become an engineer. And I moved into, I was able to sweet talk a professor in Houston to allow me to follow him around for several months before he enrolled me in the program. In that, my first task, I'll say, was to learn homer2. And I realized that there was not much available online in the sense, specifically for people who didn't have a technical background. If you had gone through a bachelor's in electrical engineering, you probably went through MATLAB, you probably went through signal analysis and things like that. I had none of that. I had worked with tissue and I killed mice for a living. So moving into this direction was quite frustrating for myself. So this is going to be more of an introduction to how to use homer2. So in my study of homer2, I had no idea where to start. So I went to the forum, and if you haven't been there, it's homer-fnirs.org. It has actually pretty good documentation on the website, but once you have to go outside of that, which you eventually will, there's not much. They do have a forum. The forum started in 2008, I believe it's 2008, and I have read every single entry and notated it since 2008. And that was the first month or so of my program in this engineering course. I also had to learn MATLAB alongside it, obviously, and those two things coming from physiology were not very smooth going. So finally, I moved into the full homer2 code. So after I went through the forum, after I went through figuring out a little bit of MATLAB, I actually went through as many of the functions in homer2 line by line so I could actually understand these. What I realized is that my difficulty had nothing to do with the application of homer2. Like I knew what I wanted to do to some extent, but I had no idea how to do it. I had no idea what homer2 was actually doing. So eventually, as I'm coming through these codes, I actually started producing some videos, which you'll actually find links to on the NIRx website. We have videos for homer2 for our own software NIRx lab, a few that are coming out for NIRx Toolbox as well, all on the support site. So eventually these are still growing, they're still coming through, but this will be essentially a summary of all of those months of reading through forums, of all those months of reading through code. And hopefully by the end of it, you will actually understand not only how to get from A to B, but actually what's going on in the background and how to manipulate your data in such a way that you can input it into homer2. You can troubleshoot any issues you might have getting into there as well. So from start to finish, we're going to go through the basic concepts of homer2. We'll go through the user interface. We'll spend a lot of time on data format. So it's going to start with actually our NIRx data format. So whenever you record data through the NIRx systems, what the format actually outputs, or how it outputs in what format. We'll also talk about the .NIRs format. The .NIRs format is basically what homer2 wants you to have as your input. That is actually a very, very, very similar format to Ted Huppard's toolbox, the NIRs toolbox. So once you convert any NIRx data into .NIRs format, you should be able to use either or. The toolbox, I think, allows for more formats than just the .NIRs, but just know if you're deciding to use one or the other, if you want to use a mix of both, once you're actually able to convert it, there shouldn't be any issue with there. And then we'll talk about just the inputs and outputs of Homer. At the very end of this, we'll have a Q&A. Admittedly, this is a technical how-to. We're not going to be talking about statistical paradigms. And if the questions become too high in the statistical sense, we won't be answering these today. We don't feel this is the appropriate format for any type of questions in that. But if you do have any Homer-specific questions, any NIRx-specific questions, feel free to ask those at the end. This is planned for 2 hours. I bet we will beat that depending on how long the questions ask or how long the questions take. But if we do need to use the full 2 hours, we have it reserved. Also, if you do have other meetings, we understand this will be recorded. So if you have to step out, if you know people interested, we're recording the event and it will be available on the support site as well. All right, here goes. And again, Lamia will be watching for any questions. If these come up and they're needed to answer immediately, we'll try to answer them, but please give us time to get to them, and hopefully at the end we'll be able to answer most of them. Okay, so we're starting with the NIRx data format. So most everyone attending today has a NIRx system. In using the NIRx system, once you acquire data, it actually saves to a default file path unless you change that. We won't be covering how to change that here, but the default file path is actually in your C drive. It's in the NIRx folder under data, and it's organized by the date of the experiment and then the number of the experiment. So if you record multiple experiments that day, you'll have experiment 1, 2, 3, etc. And you can see an example on this third line here. So in addition, in that folder, it will be saved, all of the data is saved in specific files. There are a few files here that are, in my opinion, not necessarily of great importance to most users, but there are actually several files that are extremely important. I've highlighted the ones that I find to be the most useful to most people. You'll see a .dat, which stands for .data. That is actually going to be the recorded hemoglobin that you're viewing. in the NIRstar. So when you're recording data, the NIRx system is going to be recording raw voltage. However, when you view it as it's coming in, you're actually seeing two lines per channel, and those are red and blue. The red line is going to be oxygenated hemoglobin, the blue line is deoxygenated. Since we're recording raw voltage, in order to get to the hemoglobin data, there actually has to be several calculations done in the background. Those are based off of several default values that you likely did not change. You have access to change those, but most individuals do not. However, you can view that. Even though that's not your data of interest, you can actually view that in the .dat file. The next one is the .evt. EVT stands for events. So that's actually your trigger events. Unfortunately, in Windows automatically perceives the .evt file as the classic event log. That means that every time you try to open it, you'll get an error. So in order to get around that, you just right-click it and you open it with a notepad or WordPad. I believe you can open it with Excel as well. And you'll see on the right here in this image, we have notepad icons mixed in with Excel icons because you can use either one to open them. We'll go through the formats of those in a second. So the next one down is the .hdr, which is the header file. The header file has just general info about the experiment itself and the system used. That actually is a gold mine of information. And actually that's one of my favorites. Next down are the two big ones. So you have the .wl1 and .wl2. That stands for wavelength 1 and wavelength 2. Those are actually the raw data files that you have recorded. They're usually the largest files, and they're organized in a specific manner for time points and each channel. And we'll get to that. Finally, you have the probeinfo.map. This is used to actually specify where you've located the sources and detectors. It's a map file. And it actually has all of the XYZ coordinates for each source. Each detector has information about the channels, has all this information. If you use one of the predefined montages, which is actually included when you install NIRstar, that will automatically be created. If you decide to create your own, on the support site, you'll find a few different ways to do that. You can use NIRsite, which is a new software we've come out with. It's a 3D or 2D head that you can place sources and detectors on. Or you can actually, in the older model, you can use NIRslab, which is the probe setup utility, which is, again, 2D or 3D to set up channels and detectors. I find NIRsite a bit easier to use. It's a little faster to use, and it creates all the files that you need. So getting into specifics, the wavelength 1 value, well, if you're using any NIRx system, if it's not a laser system, you'll actually see the first wavelength is going to be 760 nanometers. The second wavelength will be 850. And again, everything else on this I've actually covered. So that is going to be the basics of how NIRx systems actually save the data. When we want to actually use Homer, we can't directly input our files into Homer. We have to actually kind of build a mashup file of all these. We have to take the data, we have to take the sources and detector info, we have to take a little bit of information from the headers, or the header file, a little bit of information from the event file, and we have to mash it all into one file. We can automatically do this through NIRstar. If you go to the File Options button on the main page, you'll have a pop-up come up. This is where you can actually change the file path that you save your data. You can change the prefix of your data, and you can actually select this checkbox down here with the bright red arrow pointing at it that says export data to homer2 format. This has to be done prior to your actual recording. However, there is a way to do it offline.
John, sorry.
Yes.
I just wanted to chime in really quickly. So the option that you're showing, it's really important that you run it only from the last version of NIRstar. So in there have been several versions of this conversion script, and the script is also now embedded in NIRstar. But the script that we are currently using, which John is about to introduce, is actually the only present in the last version of NIRstar. So for this to really work as expected, you have to download NIRstar 15.1. And if you want to convert offline, as John will explain now, you have to download only the last available script that is uploaded on the Help Center. So please make sure that you have the last version and don't use the ones that we had before.
Thank you, Lamia. So as Lamia said, we've worked on this script a little bit to clean up a little changes that Homer's had and to fix a few little bits and pieces. If you forget to press the convert to file or homer2 format prior to your experiment and you have your data, you can still convert it. All you're going to have to do is download what's called the Homer offline converter.m, which again you can find on the support site under the software. It's a mat file, and once you have it, you add it to your file path in MATLAB, and you click the green Run button. This will ask you to select your file folder. Once you select it, it will convert everything needed, and then you will save it as a designated name. And the extension name will now be .NIRs. In this file, they have several variables that were then created. So the main ones, as mentioned, you have an auxiliary variable, which is useful if you actually have auxiliary data that you'd like to use. That's, I'll say, atypical. It's less typical. D is now your new data set. And where NIRx format, we actually had data sets that were in two separate files. We had wavelength 1 and wavelength 2. Now the data set is actually concatenated. So now it's one data set. The S vector is actually now it's more of a matrix actually, depending on how many conditions you have, is now the event markers. So it's now a stimulus vector, and it's basically time points for your rows. And then the columns are actually each individual event. So it'll basically set a 1 in the appropriate column at the appropriate time point, and then everything else will be zeros. The SD is actually a struct, and this is actually going to have a lot of information built into it. This is probably the bulkiest thing that Homer uses. And then finally, T, you just have a time vector, which is actually just the time in seconds, which is 1 divided by the sampling rate. So the D variable looks something like this. The format is rows are your time points, and then the columns are actually the channels and the wavelengths. Let's see. So it's concatenating wavelength 1 next to wavelength 2. So now you have double the amount of columns. The S variable looks something like this lower right-hand option. So I compared these two versions up above. So the first one is our NIRx format. So this is what your EVT file looks like. The first column is going to be the frames. So basically you had an event occur at frame 253. The next event, and that was these following 8 digits are now going to be bits. The first column is the 1's place, then the 2's, then the following column is the 2's place, then the 4's place, the 8's place, 16's, etc. Excuse me, 2, 4, 8, 16, 32 in binary. Admittedly, in what I'm used to, this is backwards binary to me. So this first row is actually event 1. The second row down, if you see 4 1's in a row followed by 4 zeros, that's event 15. So you'll see it's event 1 followed by 15, then event 1, then 15, 1, 15. This is from a typical built-in finger tapping experiment that you can find in NIRstar, which is a whole nother story, but that is actually automated in this. So that is the NIRx format above. What it converts to in the .NIRs format is now you see this matrix here below. The time points are actually going to be the total number of time points that you have in the experiment. The columns now are not in binary. They're actually, I don't know if you guys can read it, but it's 1503 by 15. The reason it has 15 columns is because in this above format, in the NIRx format, we had event 1 and event 15. So it actually has 15 separate columns, assuming that there are 15 separate conditions. So here's the SD variable. The SD variable admittedly steals most of this information, or could steal most of this information from the header file. So it's kind of a NIRx version of the header file. Within the SD variable, it's a struct, so there are actually several variables within it. You have what's called the mesh list. You have a lambda, which is just wavelength 1 in our case it's 760 nanometers. Wavelength 2 is 850 nanometers. You have the source positions and the detector positions, which are just the XYZ coordinates. You have the number of sources, the number of detectors, the spatial unit, and it has to either be centimeters or millimeters. If you plan on using Atlas Viewer, which again, whole nother story, you do need it in millimeters. And then you have Xmin, Xmax, Ymin, Ymax, which has to do with actual plots. Finally, you have a mes list act, which is the basically which channels that you're actually considering active, and then mesh list viz. These are actually interactive with the user interface, which I'll cover in a little bit. It basically is saying which channels are you actually viewing in the plot. So this mesh list variable, in my opinion, is the one that most people find the most confusing of all these. I think the rest of them make fairly good sense. Lambda would be the wavelength, source position is XYZ coordinates, etc. So the mesh list is the number of channels by 4 columns. So each row is going to be a channel, and each column is going to be is a total of 4 columns. The first column is your sources. The second column is your detector, and it's only indicating the source and detector which you consider to be a channel. The third column, I don't really understand why this is the case, but Homer decided to have a third column. I assume they were planning on using it down the road, but it is always 1. It doesn't indicate anything, it doesn't turn anything on or off, it's just always 1. And then the fourth column is going to be what wavelength you're on. So again, our data set was wavelength 1 concatenated with wavelength 2. The mesh list variable is going to now be the first 20 columns are wavelength 1 if you have 20 channels, and then the following 20 first 20 rows will be wavelength 1. The following 20 rows will be wavelength 2, and that's if you had 20 channels. If you had 40 channels, the first 40 would be wavelength 1, the second 40 would be wavelength 2. Okay, so this is a pretty easy one, but we'll get on to finally using Homer. So if you haven't downloaded it and you need to, you can find Homer on the NIRx website, and it comes in both an executable format and a MATLAB script format. The MATLAB script format, I think, is now called source. They just call it version 2.2 source or 2.1 source. The executable is the most current version. I highly recommend, if you have any interest in MATLAB or any knowledge in MATLAB, download the script version because of 2 reasons. One, you can actually see what's happening, so you actually know what you're doing to your data. And secondly, you can actually call the scripts outside of Homer. So you can use this in some other analysis format or software, however you want to use it, which I find very useful. So the GUI itself, once you have it downloaded, is fairly simple. You have, let's see here, I'm jumping ahead. You have several windows. On the right, you'll see something of a grid format, and that's actually going to be the layout on the head, the montage, if you want to call it that, but it's the sources and the detectors in a 2D plane as on the head. What you can picture here in our image here is on the left, you'll see the letters A, B, C, and D, and the numbers 1, 2, 3, and 4. Letters are sources, and numbers are detectors. So A1 is source 1, detector 1, and that would be indicated as a channel.
Hey, John.
Yes.
It's me again. Just I wanted to say another thing. So the arrangement that you are displaying right now comes because it has been converted from the probe info file. So I just wanted to mention this because it's another important difference between the different versions of this conversion scripts that have been going around. So the latest conversion scripts actually requires you to have the probe info file. So John explained it previously. The probe info file is a file generated either by NIRx lab or by NIRsite, and that contains the special arrangement of the optodes. If you use the latest version of the script and you have the probe info file, the SD struct, the SD file in homer2 will be automatically loaded. So some of you maybe have been using the first available ever conversion script, which was actually written by Rob Cooper, and it's still available for download on NIRx. So this script requires you actually to create by yourself the SD file in homer2. So you would not, once you load the data, I guess, John, you will not see then this the special arrangement of the optodes.
Yes. Okay. Thank you, Amia. So this layout, if you are familiar with the built-in montages, is the basic 8 source, 8 detector motor layout from NIRStar. So the left side is the left hemisphere of the brain, the right side is the right hemisphere. Regardless of if you download the executable or the code, once you actually run the file, it looks the exact same, it performs the exact same. There's no difference between the two, aside from perhaps a few bug fixes here and there for the newer versions. So if I click on one of these channels, or in this case, 3 of these channels, I can actually view the data of those channels. So you'll see on the right, on the probe layout, I have B1, B3, and B4 all selected. And then on matching color within this data window, you'd actually now see data. So to select just one channel, multiple channels, you click, it's a little finicky sometimes, but you click between the source and detector, and to select more than one, you would shift click. That's, again, the 2D montage, the data viewer, the pipeline, which we will get to in a second. This is not the most intuitive, but once you understand, it's actually very, very simple. If I select these channels and I see, you know, this B4 is clearly blocking my B1, if I right mouse click on that channel, I'll actually remove it from view. That doesn't mean I've deleted the channel. That doesn't mean that it's not included in my analysis. It just means that I am not going to be viewing that. And you see from this slide and this slide, the only difference aside from a minor movement is I'm no longer viewing the bright pink channel. If I click my left mouse click without clicking my right, or excuse me, vice versa. Where am I here? There we go. There we go. If I do my left mouse click, the dotted line here is now slightly different. So comparing to the previous slide, I have a very, very, very small dotted line, which means it's removed from view. Now my channels turn pink, and now I have a wider dotted line. That actually means that I'm viewing it. However, when I actually go to my analysis, it will not be included in my analysis. It will actually be marked as a bad channel. So if I do have something I dictate as a bad channel, or down the road, going through this process, I find the channel to be below my threshold, I can actually both right and left click, and now it's off of my screen of view, and I'm not including it in my analysis. So not the most intuitive way to get there. However, it works quite well. You can either get the channel out of view if it's just blocking a few things, you can remove it from analysis, or you can do both. So I mentioned earlier that, let me back up here, this open pipeline in the mid left here was not so intuitive. We're going to talk about that now. So once you get Homer up and running, you figure your way around it. The main reason you're using Homer is to process your data. You want to filter it, you want to remove artifacts, you want to get rid of stimuli, you want to actually process your data here. However, Homer, it includes a default processing stream, which is almost guaranteed not what you want to use. So in order to actually create the process you want, the stream you want to process your data with, you actually have to open up this processing stream GUI, which is just one of the drop downs at the top. The layout of this is actually quite confusing. You'll see we have 3 different drag bars here, which allow me to move each of these windows individually. However, even though I'm moving them individually, it has nothing to do with changing how this is set up. So the way it's set up is this first column is going to be your output. So it's essentially a MATLAB function. Your first column is your output, your middle column is the name of the function, and the third column is actually the input. So what you see is highlighted is the Homer intensity 2OD function, which it basically is taking raw intensity data, converting it to optical density or OD. The output of that, which is to the left of it, is DOD. That stands for delta optical density. The input to that is D, and you'll see, if you remember, that is the data set. Since it's highlighted down in this bottom window, I actually see the comments that are written in the MATLAB script. These are actually the introductory comments to the function. And you'll see, first off, the format of the function, DOD equals the name of the function times the input, the exact same thing we see up above. Then you see what the description is. It converts intensity raw data to optical density, and the input is D. It reminds you what that is, and the output is DOD. Not all of these functions are, there are varying levels of comments for each of these functions. Some you'll find much more frustrating than others. To add these in, all you actually have to do is highlight the one you want, add it in, and then you organize it up and down. It does need to be mentioned here though, this function here, the Homer intensity 2OD, is almost always has to be your first function, because the majority of homer2 functions actually act on optical density, not on raw data. And that will be different depending on what analysis software you use. So this is what it actually looks like here. So here I have a very basic pipeline that you could call it. I have Homer intensity 2OD as my first step. Next will be looking for motion artifacts using the Homer motion artifact. Next, I will use the in-stem rejection, which actually takes any of the motion artifacts and looks for nearby stimuli, and if they're too close, they'll actually remove it. Following that is a bandpass filter. Finally, it does the Beer-Lambert law and converts to concentration. If for some reason I want to maneuver these up or down, all I have to do is press up or down. Finally, I would save it if it's something that I'd want to use for future. And here we go. In addition to the processing stream GUI, there's also the stem GUI. Admittedly, I have actually never used this for my own data sets. However, and I've found many other ways that I think are actually slightly easier than this. However, if you have auxiliary data that you're using as to find your stimuli markers, say you have say it's heart rate and you're looking for your heart rate to exceed a certain beat per minute or something along those lines, you can actually upload a data set, which is an auxiliary data set. You can look for a threshold value and then over a time period. So it's actually quite useful if you have, for some reason, an auxiliary data set that you're actually looking to extract stimuli from and implement it onto your NIRx data. However, the layout of this, if you can tell, is a little screwy. The window size is actually incorrect on some monitors. So you'll actually see, let's see here. On this upper left, there's actually an additional window which you won't have access to depending on your window size, which is just basically zoom or change the stimuli window. So it's not too major, however, it would allow you to actually find your stimuli a little better. This lower right is actually very unintuitive to me. However, you'll notice that I have 1, 2, 3, 4, 5, 6 lines. Those lines are actually my conditions over my data set. And it's actually not showing the data set, it's just showing any auxiliary data, which I don't have, and my stimuli. You'll notice here in the upper right, you'll see condition 1 and condition 15 color-coded. So if you recall, in the event file, it was condition 1 followed by condition 15 followed by condition 1, 15, 1, 15. This is, again, the finger tapping, condition 1 being my left hand, condition 15 being my right hand. This lower right box here, you'll see I have 1, 2, 3, 4, 5, 6. That matches the total number of my stimuli in the window. It doesn't distinguish between which type of condition it was. It just tells me I had 6 conditions. And this column 1, which I have the option to actually rename, is actually only for notes. It has nothing to do with what condition it is. It has nothing to do with anything along those lines. It allows you to input notes about each stimuli. That is all this box does. Initially I assumed that it had something to do with the separate 2 types of data, or two types of stimuli. It's only for notes. If you want to add or delete stimuli marks manually here, I can actually select time points down by this add, delete, edit stim marks at a certain time point. I can also actually just click wherever I want a new trigger. If I do click, it will actually pop up a window and I can name the trigger by a current event or a new event. Again, while this does exist, I haven't found a need for it personally. So it hasn't been something that I have found to be as utilitarian as I had hoped. Let's see, here we go. So once we have all that figured out, we've adjusted the stimuli as we needed. We've selected our pipeline. Now I actually want to run the pipeline. In order to do that, I would actually select this calculate HRF with this run session and group dropdown. If the run session or group has this double asterisk by it, that's indicating that you have not run this. If you have run it, these double dots will disappear. So it'll just indicate whether or not, if you changed your processing stream, the dots will reappear, telling you need to rerun this. If you do the run, what it's actually specifying is basically saying, for one specific group, for one specific subject, for one specific experiment, I'm going to run that. For the session, it's for one individual. So if they have multiple experiments for that, it's kind of screwy names, but it's for one individual, multiple sessions. For the group, it will actually be multiple people within that group. I believe I'll talk about this at the end. If not, we'll cover it in the questions. But the batch processing to actually do the group is quite easy in Homer, and it has to do with file formatting. And in fact, here it is. So we have, with the groups, they're going to be designated by folder, and make sure that you don't include spaces, because it is going to be calling it out of MATLAB. For the subjects, you're going to designate by the file prefix. So this gets a little tricky if you ran different subjects on the same day, but the default prefix, if you recall, is NIRx followed by the date. And finally, for the runs, they'll actually be followed by an experiment number. So in renaming this, I always suggest this to people. You have your own decision to decide on, but I always say, if you're going to change the default path and all that, create a separate experiment folder, make copies, and then rename it there. You can always change the default path. It's just something that I'm more comfortable with personally. With these runs, however, once you change the name of it, say it, subject 1 run 1, subject 1 run 2, you want them all to be named the same, followed by preceding numbers. homer2 will actually automatically decide those are the same person doing multiple experiments. And then finally, the group will be designated. Whoever you have within that folder will be decided to be a group. We're getting into the functions themselves. The final function, which I didn't mention, almost inevitably with this Homer deconvolve href drift ss. The reason it's a very complicated name is because it does many things. one of the big things, the reason it actually has this SS, this is the newest version of this function. So let me back up real quick. On the processing stream, we started with this homer intensity 2OD. That will almost inevitably be your first step in the pipeline. This will almost inevitably be your last. So this will actually make your GLM, it will actually export data values, it'll do all these things. But I do want to mention at this point, there's this SS at the end. This is a new implementation that they put in. And what it does is actually select for short channels, and it's called short separation. In inputting when you call this function, there will actually be several input variables that you have the ability to adjust. These are going to be row SD SS threshold. It's basically saying what is going to be the difference between the distance between a source and a detector in millimeters that you will draw the line at, deciding that that is a short channel. The default is 15 millimeters. And it's worth mentioning here that we actually have these new short channels that actually have 8 millimeter separation. So if you designate a separation of, say, under 10 millimeters, and your SD struct is written correctly to indicate that these are 8 millimeters apart, then these will be selected as short channels. The next input would actually be how you want to actually regress the short channels out. And you have 3 options as indicated here. If you select 0, it will be a nearest neighbor, so basically the closest short channel. The second one is going to, if you use the number 1, it will do the greatest correlation between the channel and one of the short channels. And then if you select 2, it will be the average of all short channels for all regressions. So that is going to be kind of how that's indicated on that. Once, and I mentioned that here because this function call will actually be where you get your output from. So where everything else in here is going to be a kind of a process, and it's going to be taking the output of one function, putting it into another function, and moving it down the list. This you will actually have values at the end that you can use, and we will get to those at the very end here, which we're coming to. Also backing up. So when you actually go through Homer, with other softwares, you typically make an additional file. You don't change the file. With Homer, you're actually resaving to this .NIRx file. So you're actually creating new variables that's being saved in this .NIRx file. And the .NIRx file is in fact a mat file. So when you actually want to open it to actually see, okay, I ran all my stuff, where did it go? Well, you have to go find add this .NIRx file to your MATLAB path, and then all you have to do is call this function here. It's just load, you put the name of the file, .NIRx, and it's -mat. When you load that, you'll actually get all of the variables saved to your workspace. The main variables that will actually be of interest to you, since you're not so much concerned with your raw data anymore, you've run your pipeline on the raw data, you've done all these steps through this. You want to know, first off, what was the process that you used, and what did you obtain out of that? So you have these two, again, they're going to be 2 structs. One is pros input, one is pros result. So the pros input will have all of the functions used in the pipeline. So again, it would be the intensity to optical density, the filtering, the motion artifact remove, all those things in it, also containing the variables you put into those. The process result will actually now contain your beta values. It will also contain your R's. It will contain all the information about your GLM. And again, that's going to be if you use this Homer deconvolve HRF drift SS. If you use anything else, say just a general block average, your output will be different. You'll actually have several empty variables in regards to betas and things like that. So these are the actual outputs. Once I run all this, this is what comes out. So the first one is DOD, any of these initial D's just stand for delta, so change. DOD is going to be delta optical density, which is now basically saying, okay, it took the raw data, it converted it to optical density, which is a unitless relative change, a normalized change. The next one down is DC, which basically took the optical density and actually turned it to concentration using the Beer-Lambert law. So now you have relative change in hemoglobin concentrations. I'm going to skip over the non-bolded ones because they're of a little less interest. The DC average is actually going to be the delta concentration average, which is essentially going to be your HRF once it's reweighted and everything. But I'll touch on that down the road here. The DC average STD is now going to be the standard deviation of the delta concentration, of essentially the HRF. The DC sum of squares, sum 2, is the delta concentration sum of squares. And then down at the bottom, the two ones that I find a little bit more interesting than the less bolded ones is DC residual, which now is the delta concentration of the delta concentration residuals, and the beta values. So these are what they look like. So DOD, again, is delta optical density, the change in optical density. You'll see that in the upper left. That is for all of my channels over my entire time course. What you'll see is those are zeroed out, and they're normalized. They're now a relative change. The concentration is this lower right. So it took the optical density, took all my input values for the Beer-Lambert law, and has now converted the relative unitless changes to relative changes in hemoglobin. And again, these are over the entire data set. The DC average is a 4-dimensional function variable, and it's the time points by the hemoglobins, and those are, I think, only the oxy and deoxy. They do not include total, whereas some of these other variables do include total. So that would actually be, so that our second dimension here is 2 and not 3. The third dimension is the number of channels that you had, and then finally the number of conditions. To plot the HBO and the condition, you can call this function right here, which is just plot process result dot DC average, and I'm doing all time points, HBO, all channels, condition 1. This is very dependent on the basis function that you use. So this will be, obviously, you need, take some a priori knowledge of your population, of your task, of all that, to use the proper basis function, which we'll cover in a little bit. And I think we actually have another talk on that as well. I want to show you in these two, because this is actually the same data using completely different basis functions. Clearly, it will matter. You have quite different, you still have a peak value nearby. This one's around, around 80 frames, I believe it is. And here we're at about 110. It's close, it's not that close, and then clearly the data itself is quite different. And also it's worth noting that the units of change in homer2 are micromolar. So the DC average STD is the standard deviation, and it gives the standard deviation compared to the HRF. Again, it is very model dependent, but it's very similar in format to the previous variable. So you have, instead of total time points here as your first dimension, you are only looking at the HRF. So typically that's going to be like -5 seconds all the way up to 30 or 35, somewhere around there. Whereas the previous, excuse me, I believe, sorry, we are correct on both. They're both HRF time points. There are other variables that we'll cover with full time points. So again, though, that'll be that window that you designate to be your HRF window, or your block average window, essentially. Followed by the hemoglobin species. Again, it's going to be HBO and HBr, or oxy and deoxy, the number of channels, and then the number of conditions. Again, to plot the oxyhemoglobin and condition 1, you would use the following call in MATLAB. And again, always keep in mind it's very, very, very dependent on the basis function selected. The sum of squares, again, very similar, 4-dimensional variable, same exact format, and to call it almost the exact same function call. And actually, I have an error here. This should actually be DC sum 2. The DC residual is actually somewhat less intuitive, I'll say. So it actually plots the entire time course. However, you'll notice, so I want to mention here, so the formula is right here. It's just basically y minus y hat divided by the standard deviation. It will only differ from DC, the variable DC, during your actual experiment. So here I have my entire time course. My experiment was only from this mark here all the way to this mark, and you'll see the difference in blue. So the red actually, there's no difference essentially because we had no model to compare to during that time. We only had the model during the experiment. So this will basically compare the HRF to the data itself here. Again, to plot, and again, I apologize for my error there. That should be DC resid, not DC average. But the format is now no longer HRF time points, but all time points times the HBO and HBR by the channels by the condition. And then the beta values. So the beta values are usually what everybody's going after. These are actually going to be a little tricky because if you use, say a colleague of yours used a different basis function than you did, you may have a different number of betas. So the format here is actually going to be 4-dimensional again. And the first, the rows essentially are no longer time points. They're specifically the number of functions that were used. So if you had a basis function which included 4 functions within the time window, the HRF window, you will have 4 as your number of rows. The number of columns is 2, and it's just oxy and deoxyhemoglobin in that order. Then then your third dimension is actually going to be channels, 4th dimension is condition again. So a little tricky in that sense that if you use a simpler basis function, you could essentially extract 1 beta. If you use a more complex basis function, you may have many, many beta values. Let's see here. Yeah, as I mentioned there. All right, so we're closing up here. We're just coming in on the hour. I do have a few extra points that I want to mention that are definitely worth noting. So if you actually want to export your results outside of the .NIRx file, say you want to actually export your mean results, you can actually do that just with calling this export mean results button in the file dropdown. Another way to actually take out just the betas, it's a little tricky, but you can actually use this function here, which is DLM write, the number of the file you want to save it as, the variable name, in this case I saved the betas as BTA, use a delimiter of some type, in my case I used space, and that should be appropriate. The format gets, in my opinion, much trickier than the MATLAB format, but that actually will allow you to export the file itself as a text file and get all those beta values out. The mean results, if you use this export mean results, automatically saves as a text file. You do have to input what time period you want to average. So say you're looking for peak values or something like that, or you want the entire block average, you would actually indicate the starting and ending time of that block. When you're viewing the data in homer2, the thing you will actually, so once you actually run the pipeline, you have 3 different views that you can see. The first is raw voltage, that's just your raw data. That is the automatic thing when you click on one of the channels in the montage that pops up, you see raw data. Once you run your processing stream, it then will allow you to also view optical density and a hemodynamic response function, or HRF. The optical density, again, as we showed earlier, is relative change in values. The hemodynamic response function that is actually plotted is not going to be the basic function. It's the function convoluted onto your events and then also weighted using the beta values. So you actually get a comparable view of channel by channel based on essentially your betas. But again, what is plotted is very, very dependent on what you put in as your variables. You know, if I use completely unrelated variables, I will have a completely different plot. Also, I want to mention, once you pull these up, you will have the option to select many different variables. I do just want to cover the more common ones that aren't necessarily well documented. So often, homer2 is kind of notorious for its artifact correction. You have about, I think it's like 6 or 7 different ways to correct for motion. The basic one is this artifact. It's Homer artifact, motion artifact. The input variables, the first one is T motion. What it means is basically I'm going to select a amount of change that I want to consider, you know, an amplitude change or a standard deviation change that I'm going to consider to be noise, but I also have to select a time window for that change to occur. So basically saying if I select a 10-second time window, I would just expect a lot more change. But if I put a half a second time window, that same amount of change is more likely to be a motion artifact. So T motion is the time in seconds to consider a motion artifact. T mask is basically saying if I do find and pinpoint a motion artifact, how many seconds before and after do I want to correct for? Usually I think that's 1 second or so, I think is the default. The more interesting input on that is the ST dev threshold, which is standard deviation threshold. All that is saying is how much of a standard deviation change over my T motion time do I want to actually consider to be a change. Amplitude threshold, the one below it, is saying how much amplitude of change as opposed to standard deviation of change do I want to be associated with artifact. What's tricky with this is you really more than likely want to use one or the other, not either standard deviation threshold or amplitude threshold. Using both may be overkill. I'll leave that up to you guys, but in my opinion, that's probably overkill. If you only want to use standard deviation threshold to rule out amplitude threshold, you just put in a ridiculously large number. So it is unlikely that it will change 100 units over half a second. It is extremely unlikely that it will. So I can put 100 or 150 or 1,000 or something, some very large number. Do the same thing for standard deviation if you don't want to use that. You just put in a very, 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 very large change. Homer OD2 concentration is going to be your Beer-Lambert law, and it uses PPF as opposed to NIRx, which uses DPF. PPF is the partial path length factor. You may have to do a little research on that, but if I recall correctly, it's something of like 1/50th of the DPF. If I received that from Dr. Huppert of the NIRx Toolbox and fame. But finally, it's going to be this Homer deconvolve href underscore drift SS. The inputs for those are probably the most important and also allow you probably the widest range of change for your results. The first input is T range, which is just the time window that you're using as for your block average. Usually it's something like -5 to 30 or something along those lines. The GLM solve method is basically how are you going to solve for your betas. You have the iterative weighted least squares, which is, I believe that was from also a Huppert paper. You also have the ordinary least squares. So you have 2 options. You call that using a 1 or a 2. Which is mentioned actually on the function itself. The IDX basis is what basis function. In my opinion, this is one of the most important inputs on this. You have a selection of probably, I think it's 5 different basis functions to choose, each of which have different inputs. Usually you'll use something like a Gaussian or something similar. But you do have a wide variety to choose from on that. That will take a little bit of research, but if you use I believe it's the Gaussian on this, you also have to put the inputs to the basis function. These, I think, are probably the least well documented for homer2. You'll typically have inputs of standard deviation and step, which standard deviation is obvious. It's going to be the standard deviation of the width of your function. And step is actually how separate are the mean values of the functions. That is one option. This one I have indicated here is probably the more widely used. You actually have 3 inputs that are solely listed as tau, sigma, and t. They don't include anything else along those lines, just tau, sigma, and t, and what the typical values are. What these are, tau is going to be what is the onset delay of your function? What is the expected delay of your activation? Sigma is the width of signal. So I believe it's the max width at half max. The t is going to be the length of your stimulus. So that's essentially your boxcar. If you have a 10-second stimulus, it's going to be 10. So changing those 3 inputs will actually change your shape quite a bit. You also have the option to do 2 of them, because you have the option to do 2 per, I believe it's, what is it? 2 per wavelength or 2 per hemoglobin. I can't remember which it is. If you input only 3, it will double that and assume it's the same across. But you can differentiate between the 2 if that's of interest to you. Finally, in this function, it is called the homer deconvolve href drift. You do have the option for drift correction, which is basically correcting for any slow artifacts in your experiment. It's a polynomial correction. The default, I think, is 3rd order, so just number 3. It is well worth figuring out if this is something that you need or not, because you can actually correct for something that's not there depending on if you have a shorter experiment or something like that. I have done that, and the results are pretty entertaining if you plot them. All that said, that I hope answered some of the background questions in homer2. I know there's a lot out there that it covers a little bit more on the statistical side of things, but that was kind of what I found to be lacking in the field for YouTube videos and tutorials and documentation. If you guys do have questions, I think we had quite a few that were answered.
Yes, there are a few questions. I don't know if I think you did not answer.
Got it.
Some of them, yeah.
Okay, so the T and F contrast, this was actually frustrating to me. I think in the past you could, and I think they actually removed that. So I have dug, and even in the forum, I believe it was answered either a video or a forum, they keep talking about re-implementing it, but from my understanding is you have to extract your betas and actually perform the t-test yourself. So the actual full-on analysis, I believe, is actually done outside of homer2, and homer2 is meant for just the processing aspect. That said, the documentation has been not definitive on that. I have dug and not been, and I've asked around, and I haven't been able to find where or how you would calculate those. Let's see, pick your own baseline when calculating DOD. The default is used as a negative second. So you actually calculate it based on how many seconds prior to an event. Excuse me, no, that's for the HRF. For the DOD, it is calculated as a mean value of the total data set. If you wanted to change that, I have never done that, but I believe you could probably do that in the intensity to OD function, which is actually, I think it's only 3 lines of code. So all it does is calculate calculates the mean of the data and then does an inverse log of the change compared to the mean. So all you'd have to do is alter that mean.
Is this the baseline that is used basically before computing the Beer-Lambert's law?
Yes, yeah. They actually do it separately.
It's the same as in NIRx lab. Yeah, you can set. So it's not really the baseline. It has nothing to do with log averaging. It's basically the baseline that defines what is then your zero. And in NIRx it's the same. So the default value is basically the entire duration of the data set, but you are free to change it. And a lot of people prefer to set it simply to the period before the first event started. But to be honest, I tried to do a couple of tests changing this because the question came up very often, you know, how exactly should I set it? And I tried very different values and the difference was actually minimal. So I don't think it's actually very important.
That is very interesting. But if you did want to change it, I think you would have to go into that code. It would be quite simple. You just alter where they calculate the mean, which is one line of a 3-line function.
There is actually a fun story. So once I asked our physicist here in development how exactly is the zero determined, I was like, okay, so is the mean value of this baseline basically the zero? You know, so we have positive and negative concentration. So it's basically the, you know, how do we define the zero? Is zero simply the mean value of this baseline? And he said, well, yes, almost, but not exactly. I will write you a few sentences on that. So the result of that is actually a 10-page document that you can find on the help center. I don't think it makes a difference. Of course, it refers to the way it's implemented in NIRx, but it's the, you know, it's the Beer-Lambert law. So if you're really interested in how the choice of the baseline affects then the zero of your concentrations, if you're brave enough to read this 10-page document written by a physicist, you can download it from our help center.
All right, so the next one is, where can the length of stimulation be set? So that was set actually in the Homer deconvolve href drift SS function, and that was actually the capital T variable input to the basis function. That is essentially the stimulus length, which is, it's actually dependent if you use, I think 3 of the 5 use this variable, 2 of them actually don't use that. They calculate in a different way. All right, so I think that answers the questions. I do hope, Lamia, did you have any questions?
No, I was actually, so if the very first time I used Homer, actually the first couple of times, I never even realized there was this, how do you call it, this stream where you put all the functions. So I just clicked on run, and I was wondering what I was doing with that. So basically it loads the default processing stream.
Yes. Yeah, and that's probably not what you want. It's pretty limited. And actually, if it will ask you to load a processing stream, if you don't have one, you click cancel and it will load this default. You can make the processing stream whenever you want. So you know, even if you've already rerun your data, there is actually a file option to reset your data. So if you've run it and you want to change that, you just reset it and run it again. That said, it's never changing the D variable, which is your data. So more than likely, you can get away with not resetting it. I mean, I'd say that with caution, but the original data set is always still there. So you just get different results each time.
I did want to use the opportunity to talk about the DPF and the PPF, exactly because this question has come up to our support team for a couple of times in the last few weeks. So there is a difference between the DPF, differential path factor, that is used in NIRx lab, and the PPF as used in homer2, right? And in the NIRx toolbox that is developed now by Ted Hubbard. So this factor basically describes you what is the distance. So for example, if the distance over the scalp between source and detector is, let's say, 3 centimeters, then the distance that each single photon travels within, inside the volume is DPF times that distance. So DPF times 3 centimeters. So the standard DPF is around 6 centimeters, which means photon travel almost like between 8 and 12 centimeters. So the DPF affects the results very much. So if you change, the DPF depends very much on the wavelength. It also depends very much on the age of your subject. So right now, I don't know if in homer2 there is this function, but if not in homer2, you can implement it anywhere. You can calculate the dpf or ppf by basically, there is a formula that helps you calculate it based on the age of the subject. And it also varies a lot based on the wavelength. And I've seen that the default values in homer2 for the ppf, which is basically the partial differential path factor, basically the amount of photons that travels not through every volume, but only through the brain. So the default values, if I remember correctly, are 6 and 6. Same for both wavelengths, which is actually quite wrong if you keep it. If you keep the default values, it can affect your results very much. So we have noticed, for example, that if you change the SD distance, that affects your data, but only in a quantitative way. So the data will still look the same, only the amplitude will change. So basically the waveforms are not changed. If you change the DPF, you can even completely produce, so let's say if you play with these two values, the DPF or PPF for one wavelength and the other, you can produce, contrary results. So I just wanted to mention this, that these values have to be, taken or chosen carefully, and don't keep the default value as in homer2. There was also a lot of confusion before because the toolbox by Ted Huppert uses a very different DPF, which is basically 6 divided by 50.
I think I recall that. Yeah, that's what I had mentioned earlier.
Yes, exactly. So because what Ted Huppert explained is that this is, again, a PPF and not a DPF. So basically, it calculates the percentage of the volume traveled by the photons only through the brain and not through the whole every other structure. So that's why it has to be divided, because it's only percentage. So it's 6 divided by 50. But to be honest, I still do not understand why then in homer2, which also uses the PPF, it's used 6 and not 6 divided by something. Mm-hmm. So I think this topic is still a little bit unclear. Yeah.
Okay, well, I want to thank everybody for coming. I know we're well before the 2-hour limit. I was expecting to be about this time. I just wanted to make sure we'd rather go under than over. We do have other videos and other documentation on homer2, which is more kind of on the surface rather than in the background. I was hoping that this would add to that. But thank you guys for coming, and I hope it was useful. And if you guys do want to reference back to this, whether it be for formats or something like that, we will be uploading this video to our support site very soon. So give us probably just a few days and we'll have it up on the website.